Welcome! In this elementary calculus tutorial, we are going to solve a few problems to do with basic triangles. We're going to plot sine and cos. We are going to prove some basic trigonometric identities. We're going to express some angles in radians and express some angles that are presented in radians in degrees. We're going to differentiate some trigonometric functions, and you can see some of these will involve the chain rule and the product rule. We're going to use the quotient rule, and then we're going to look at implicit derivatives. Okay, so if you're interested in that, then stay tuned. We're also going to plot a few things with Mathematica after I draw them by hand, just to make sure that I got it all right. Okay, so let's begin, starting with question 1. Solve the right triangle with angle A equal to 78.7 degrees, side length A opposite that, 7600, C is the hypotenuse, and so solve here means find all the interior angles and all of the side lengths. Okay, so the first thing we might want to do is find the hypotenuse C. This uppercase C, incidentally, is 90 degrees because this is a right triangle. Okay, so let's find lowercase c, the hypotenuse length. So to do this, we use sine of uppercase A is equal to lowercase a on C, opposite on hypotenuse. And so we want to find lowercase c. So rearranging this equation, we multiply both sides by lowercase c and divide both sides by sine of A. So we have c equals A over sine of A. And so that is 7600 over sine of 78.7 degrees. Okay, and so to find this side length C, I need to calculate this in a calculator, or in this case, I'm going to use Mathematica. So let me do that here. First, I need to make sure that I can calculate a sine in degrees. So I'm going to calculate sine of 30 degrees to make sure that I get 1/2. Okay, so I've calibrated. I know that that's correct. So that's the correct procedure. So now I will enter 78.7 degrees. And I've got 0.980615 and so on. And so this is my denominator. So now I need to take 7600 divided by that, and this should be my angle, or my side length, sorry, C. So this is 7750.24, but I can get more digits by just pressing the enter button here. So 1, and I'll stop at 3 decimal places. Why not? Okay, now that we've got C, we can find B using Pythagoras' theorem. So by Pythagoras, we have a squared plus b squared is equal to c squared. We've just calculated c squared and we're given a squared. So b squared is c squared minus a squared. So b is the positive square root of c squared minus a squared. In this case, we've got the square root of 7750.241 squared minus 7600 squared. And so let's calculate again. Okay, so I'm going to square that number, subtract 7600. Let's see what we have. Okay, then I'll take square roots. And we get 7749.75. Let's get another decimal place on that. If I round that fourth decimal place up, I get a 1 in the third decimal place. All right, so this is our B. We found C as well. And so the last thing missing is the angle B, opposite side length B. And so for this, I can use sine, cos, or tan. So let's go ahead and use cos. So cos of B is adjacent on hypotenuse. So we've got 7600 over 7750.241. Okay, and so now I want to take the inverse cosine of this ratio. So I will write arc cos, but if you're doing this on your calculator, then you will use the, I think it's a shift button or a, yeah, it's probably the shift button to calculate cos superscript -1. But it's also known as arc cos. Okay, so I'm taking arc cos of this ratio. And so I get this in radians. So B equals 0.1972. I'll just write radians here, but now we need to convert this to degrees because this angle right here is given in degrees. So I want this in degrees as well. So to do that, I need to multiply by 180 degrees divided by pi radians, so that my radians unit cancels. And so we get 11.3 or 11.2999, but that does give us 11.300 if I round that to 3 decimal places. Okay, and so we've solved the triangle because we have all 3 angles and all 3 side lengths. All right, so that was question 1. Let's move on to do question 2. So solve the right triangle with B equals 32.1 degrees A is something we've got to find. Okay, side length C is known as 23.8. That's the hypotenuse, and B is unknown. Okay, so we need to find angle A, we need to find side length A and side length B. So let's start by finding side length lowercase a. So we have cos of B is equal to A over C. And so therefore A is equal to lowercase c cos of uppercase B. And so this is 23.8 cos of 32.1 degrees. Okay, so I'll get on my machine, type in 23.8 multiplied by the cosine of 32.1 degrees. And I get 20.1615, but I'll just round this up to 20.162, putting it in 3 decimal places. Okay, so now that we have that, I can do the same, or almost the same, using the sine, or I could use Pythagoras' theorem. But here, let's just use sine of B is equal to opposite over hypotenuse. And so now lowercase b is equal to c sine of b. So we have 23.8 sine of 32.1 degrees. Okay, and so I'll enter that in. Just copy and paste this, but I'll change my cos to sine. And so I get 12.6473 as b. Okay, fantastic. So what are we missing now? We're missing uppercase A, but the sum of the interior angles of a triangle add up to 180 degrees. And so we know that C is 90, so the sum of A and B adds up to 90 degrees. And so we know then that A is equal to 90 degrees minus 32.1 degrees. And so let's work out what this is. 90 minus 32.1 is 57.9 degrees. Okay, and so now we have completely solved the triangle, so let's move on to the next question. Question number 3. Solve the triangle with lowercase a, lowercase c, and that's all we're given, other than we know that it's a right triangle, so we do have one interior angle as 90 degrees. So we've got C is 12.63, lowercase a is 9.908, and we want lowercase b, and we want angle b. Okay, so let's use sine of... No, not yet. Not yet. So we need this, because we don't have uppercase A or uppercase B just yet, so we need to use Pythagoras' theorem. First, which says a squared plus b squared equals c squared. Okay, but we're after b, so b is equal to the positive square root of c squared minus a squared. And so that is the square root of 12.63 squared minus 9.908 squared. Okay, let's simplify this. And we've got 7.83252 and so on. So I'll chop it off there. So this is B. So now we've got all of the side lengths. So how would we get the interior angles? Oh yeah, we can use sine there, right? So sine of A is A over C, and so uppercase A is the inverse sine, or arc sine of A over C. So arc sine of 9.908 over 12.63. But on your machine, you've got sine superscript minus 1, which you would access with the shift button if you're using a calculator. All right, let's do this in Mathematica here. Arc sine 9.908 over 12.63. So I get this angle in radians, but I need this in degrees, presumably. So let's first put 0.902 radians. And let's also give this in degrees by multiplying by 180 over pi. So 51.673 degrees. Okay, now to get b, uppercase B is just 90 degrees minus 51.673 degrees. So I'll take that and write 90 minus that. And so we've got 38.327 degrees for B. All right, great. Let's move on to question 4. Plot points of sine of x by evaluating points x sine of x for several x. Now that should read over here x belonging to, or x equals pi on 4 times k, where k is an element of the set of integers. Okay, so I'll rewrite this question. So we've got to plot y equals sine of x via points x comma sine of x for x equals pi on 4k, and let's just take k equals, say, minus 2, minus 1, 0, 1, and 2, for example. Okay, so what is this then? So x equals minus pi on 2, then we have minus pi on 4, then we have 0, then we have pi on 4, and then we have pi on 2. These are all in radians. Okay, so let's find a few of these points. So when x is minus pi on 2, we've got sine of minus pi on 2. Okay, and so this is sine of minus 90 degrees, but we can represent this as sine of plus pi on 2, because these are the same. Now sine of 90 degrees is 1, isn't it? All right. So this is minus pi on 2, 1. Okay, and then next we've got minus pi on 4, sine of minus pi on 4 equals minus pi on 4, sine of plus pi on 4. Sine of pi on 4 is sine of 45 degrees, and this is 1 on root 2. Or root 2 on 2. Okay, next, x is 0, so we've got 0 sine of 0. But sine of 0 is 0, so we've got the point 0, 0. Okay, sine of pi on 4, we've already calculated that, it's 1 on root 2. And then finally, pi on 2. So we've got 1 for that y coordinate. Okay, so now that we have a collection of points, let's plot our function y equals sine x. I'll grab my ruler so I can try to draw a neat version of this. There's my x-axis. Y-axis. Okay, now I've gone out to pi on 2 on either side, but we know there's a fair bit more. So let's put pi on 4, pi on 2, which is where I stop there. Let's put 3 pi on, no, I want pi, yes, okay, pi, and out here I want 2 pi, because sine is periodic of period 2 pi, and then here, okay, so that's probably good enough for there. Now we know sine starts here at this point 0, 0, and it comes up and it meets 1 at pi on 2, right? So we need a 1 on our y-axis, and let's put our point here, and I'm talking about this point. Okay, so then 1 on root 2 is about 0.7, so it's up a bit right about here. Okay, and then what happens is sine comes back down to 0 at pi, so we've got another point here, but there's a little bit of a symmetry about x equals pi on 2, so I'll put another point here of equal height. Okay, then it eventually goes down to -1 and then back up. And so I'll connect the dots at this point. So sine looks something like this. Now let's do the other side. So minus pi on 4, minus pi on 2. So it meets -1 at minus pi on 2. So this is the bottom there. Minus 0.7 at minus pi on 4. So 1 on root 2 is the y value. Oh, these should be minus. Yeah, so sine is an odd function, so that minus comes out. So these minus come out, so that's -1. That minus comes out, and that's minus. It's a minus there as well. Okay, so let's keep going. So something like this. And then we come back down and meet the axis at minus pi. And then it comes up and keeps going like that. Okay, on this side it keeps going as well. Now let's do a mathematical plot of the sine function. So I'll go from minus pi to 2 pi. Okay, so you can see what we have here. So that's more or less what I've drawn. I've taken this a little bit more to the right there in my drawing. Okay, so here's the sine function. So let's move on and do question 5. Okay, except this time I think I'm going to use Mathematica to help me out to evaluate the points. So what I'll use is table x comma cos of x and here I'll replace the x with pi on 4 times k, and then I'll just tabulate this over k. Okay, so here you see I have a list of points, and so you could do this by hand just by using your calculator. Now if you wanted a calculator value of this, as in approximated value, I could just put in 1.0 and get numerical approximations of these. Same thing for the x-coordinate. Okay, so now I've got some numerical approximations of these, and this is what you might do on your calculator. Okay, and so now that we've got this, I'll put this in memory, and then I'll plot that by writing list plot. And let's call this B. Okay, so we have a bunch of points, and this is what you would find by hand. So now that we've got those points, let's also include the plot of the cosine function. And then I'll call this G, and then I want to show the two of these together. Now I'll suppress the output of A. Okay, so I need to take this back to -5. And this is what you might end up with. So we've got a plot of cos. We've got all the points we were asked to compute. And so in this hand calculated exercise, what you're meant to do is find the points using your calculator, fill them in on the graph, and then connect the dots, filling in a cosine wave. Okay, now question 6. Question 6 is fairly similar. So again, I'm just going to use Mathematica to do this. But what I'm going to do is just modify the code that I have already written and change this 1.0 to a 3.0 and put a 3 in front of the cosine. Okay, so what it's done is it's just magnified the amplitude of the wave. So you see it now goes up to 3 and it goes down to -3. Okay, let's move on to question 7. Plot the points of y equals -4 sine x in the same way. Okay, so let's just do that. We'll put in a -4 here. And then I will change this to -4 sine of x. Aha, I didn't change that cos to a sine. Okay, let's do that. So there we go. So this is a plot of -4 sine of x, done in the same way. All right, next question is question 8, which says prove sine x over tan of x is equal to cos of x. Okay, so for this one, I think we can assume that tan of x is sine over cos, but let's just draw a triangle. Here is x, our angle x. Let's assume that it's a right triangle. And then let's call this side length A, C, and B. All right, so here we have, let's first write cos of x. That's adjacent over hypotenuse, so this is B over C. Okay, next, sine of x. This is opposite over hypotenuse, that's A over C. And tan of x is defined as opposite over adjacent, so A over B. Okay, now we're asked, what is this ratio? Is it in fact cos of C? Well, let's have a look. So sine of x divided by tan of x is equal to, in this case, we have A over C all over A over B. Okay, so if we multiply top and bottom by C and multiply top and bottom by 1 on A and multiply top and bottom by B, we will end up with B over C, which is in fact cos of x. All right, but you can do this alternatively by saying sine of x over tan of x is sine of x over the ratio sine of x over cos of x and then multiply top and bottom by cos and multiply top and bottom by 1 on sine, and you will get cos of x. Okay. All right, let's move on to question 9. Prove that sine of x sec x is tan of x. Now sine is 1 over cos, right? So let's write sine of x sec of x is equal to sine of x times 1 over cos of x, because that is the definition of sec of x. And so we can write this sine over cos, which of course is just tan of x. So that one was incredibly easy. All right, so let's move on to question 10. Prove that cos squared of x minus sine squared of x is equal to 1 minus 2 sine squared of x. Okay, so the thing that comes to mind here is that cos squared plus sine squared is equal to 1. So we'll say since cos squared x plus sine squared x is equal to 1, it follows from this that cos squared x is equal to 1 minus sine squared x. So then cos squared x minus sine squared x is equal to 1 minus sine squared x minus another sine squared x. So what I've done is just substituted this in here, and that's this. So let's put a bracket around that, and then we have this. Okay, now if I take the brackets off, you see you have 2 of these minus sine squared x, so we clearly have 1 minus 2 sine squared x. And that completes that proof. Okay, let's move on to question 11. Express 15 degrees in radians. Well, what I need to do is say that this is 15 degrees multiplied by pi on 180 degrees, so that the degree unit cancels. And then I need to simplify this ratio, 15 over 180. So if I put this in Mathematica like this, it will simplify that fraction. And so we have pi on 12 for that. Okay, so let's do the same thing with 120. 120 degrees is equal to 120 degrees times pi on 180 degrees. And so canceling the common 10 factor, and there's also a common 3 in there. So 12 over 18 is 2/3. So 2 pi on 3 radians. Okay, question 12. 210 degrees is equal to 210 degrees times pi on 180 degrees. So 21 over 18 is 7 on 6. So this is 7 pi on 6 radians. Okay, 99 degrees is 99 degrees times pi on 180 degrees. So let's reduce the fraction 90 on 180, or 99 on 180. So we have 11 on 20 pi radians. Okay, moving on, converting the other way. question 13. 3 pi on 5 radians is equal to 3 pi on 5 times 180 degrees on pi radians. So the pi unit cancels. And so then we have 3 times 180 over 5 degrees. So let's put this into the machine and simplify that fraction. And we have 108 degrees. Okay, but if you were going to do this by hand, the way you would do that is divide that 5 into the 180, because that will be an integer, and then multiply the resulting integer by 3. Okay, next part of this, 3 pi on 2, convert this to degrees, so 3 pi on 2 multiplied by 180 degrees on pi. So we cancel the pi unit. Half of 180 is 90, so this is 3 times 90 degrees, which is 270 degrees. Okay, question 14. 3 pi on 10 radians is equal to 3 pi on 10 times 180 degrees over pi. We cancel the pi. Divide the 10 into the 180 as well. So this is 3 times 18 degrees. 18 times 3 is 30 plus 24, which is 54 degrees. Okay, next piece of this, 11 pi on 6 is 11 pi on 6 multiplied by 180 degrees over pi. Let's cancel the pi. 180 divided by 6 is 30, and so we have 11 times 30 degrees, which is 330 degrees. Okay, no calculator needed for that one. Question 15. Express the following angles in radians and round to the number of significant figures given. Okay, 84.0 degrees is 3 significant figures. But in my opinion, it doesn't make a lot of sense to think of significant figures or use significant figures when you're dealing with angles. You really need to use calculus to get a good understanding of how to represent the errors. But let's do this anyway. Okay, so 84.0 degrees is equal to 84.0 degrees multiplied by by pi times pi on 180 degrees. There we go. Okay, so we have some units to cancel. So what is 84 over 180? Well, it's 7 over 15. So we have 7 pi over 15 radians, right? But now what we need to do is express this as a decimal number and then give the result in 3 significant figures. So I'll put 7.0 over 15 times pi. And so we get 1.466, but in 3 significant figures, this is 1.47. Okay, let's move on to question 16. Looks very similar. Express the following in radians, round to the number of significant figures given. Okay, sure. So 478.5 degrees is equal to 478.5 degrees times pi on 180 degrees. So I'll put this in my machine, 478.5 times pi over 180 degrees. So we have 8.3514. Now if I chop this off there, I have rounded this to 4 significant figures because we have 1, 2, 3, 4 figures. Okay, let's move on to question 17, where we start some calculus. So question 17, find the derivative of the function y equals 3 sine of 7x. So y dash of x is dy on dx, or d on dx of 3 sine of 7x. Okay, now that 3 is a constant, so that can float through this differential operator. So we've got 3 times the derivative with respect to x of sine of 7x. Now we need the chain rule. So here inside our sine function we have u. So we let u be 7x. Okay, now the chain rule says that this is 3 d sine of u with respect to u times du on dx, but u is 7x. Okay, and so this is equal to, now the derivative of sine of u with respect to u is cos of u. But remember, u was 7x, so that's cos of 7x. The derivative of 7x with respect to x is 7, but let's write that 7 over here. Okay, so here is our derivative. Let's do question 18. We have y equals 5 sine of 7 minus 3t. Okay, y dash is 5 times the derivative with respect to t of sine of 7 minus 3t. Now inside this bracket, let's let that be u, as in the whole 7 minus 3t. So using the chain rule, we have du on dt becomes, or sorry, this is d sine u on dt. Now I can introduce a du here and here, so du and du, but u is 7 minus 3t. Okay, the derivative of sine u with respect to u is cos. So we have 5 cos of u. U is 7 minus 3t. And then the derivative of 7 minus 3t with respect to t is minus 3. So now we just need to simplify. Let's pull this minus 3 over with the 5. And so we have y dash is minus 15 cos of 7 minus 3t. Okay, let's move on to do question 19. So y equals cos of 1 minus x. Okay, and so y dash is equal to the derivative of cos of u with respect to u times du on dx, where u is 1 minus x. All right, and so this derivative is minus sine. So minus sine of u, but u is 1 minus x. And then we have du on dx is the derivative with respect to x of 1 minus x. So this derivative is minus 1. So let's bring the minus 1 over with this one, and so we get plus sine of 1 minus x. Okay, great. Let's do question 20. So in question 20, we have y equals 4 cos 6x squared plus 5. Again, we use the chain rule to do this. So y dash is 4 times the derivative with respect to x of cos of 6x squared plus 5. Now let's let this inside the bracket be u. So we have 4 d cos of u with respect to u times du on dx by the chain rule. But u is equal to what's in here, so we really want this u to be represented here as 6x squared plus 5. Okay, let's finish this off. The derivative of cos of u with respect to u is minus sine of u, so we have minus 4 sine of u, but u is 6x squared plus 5. And the derivative of 6x squared plus 5 is 6 times 2 is 12x. So now let's bring this 12x over here. 12 times 4 is 48. We have minus 48x sine of 6x squared plus 5. Okay, question 21. Differentiate or find the derivative of the function y equals 3 sine cubed 2x to the 4th plus 1. So y dash is 3 times the derivative with respect to x of sine cubed 2x to the 4th plus 1. So here let u be equal to sine of 2x to the 4th plus 1. Okay, so then this is 3 du cubed on du times du on dx. The derivative of u cubed with respect to u is 3u squared. So 3 times 3 is 9, so we have 9u squared. But u is sine of 2x to the 4th plus 1. So that's sine squared 2x to the 4th plus 1 for this part of it. Now we have du on dx. Okay, so that's d on dx of sine of 2x to the 4th plus 1. Now let's let w be equal to 2x to the 4th plus 1. Okay, now we need to use the chain rule again. So this is 9 sine squared 2x to the 4th plus 1. Derivative of sine of w with respect to w times dw on dx. But w is 2x to the 4th plus 1. Okay, now the derivative of sine of w with respect to w is cos of w. So we have 9 sine squared 2x to the 4th plus 1 cos of w, but w is 2x to the 4th plus 1. And then this derivative of 2x to the 4th plus 1 is 8x cubed. And of course, 8 times 9 is 72, so we can express this as 72x cubed sine squared 2x to the 4th plus 1 cos of 2x to the 4th plus 1. Let's get Mathematica to check this. So we were differentiating. Three sine 2x to the 4th plus 1, and then I will cube that and differentiate that with respect to x. Okay, so it gives 72x cubed cos 2x to the 4th plus 1, and then we have our sine squared 2x to the 4th plus 1 in this term. Okay, fantastic. I need some more paper. And let's do question 22. Find the derivative of y equals cos squared of the square root of x. Okay, so I'll do this a little bit faster now, not necessarily setting out a u. So dy on dx. Now the u here will be cos of the square root of x. So we have d cos squared of the square root of x with respect to x, which is d cos squared square root of x with respect to cos of the square root of x. Now I'm using the chain rule. Okay, now look at this. I have not set out a u, but it's correct. And how do I know that? Well, I know that because if these were fractions, then I would be able to cancel these two and I would get back this. But they're not fractions. That is just innate to memory of the rule. So that's okay. All right, so this is the derivative of u squared with respect to u. And so I just bring down the 2, subtract 1 from the exponent. So for this derivative, I have cos of the square root of x. Now the derivative of cos of the square root of x with respect to x, I know that I need to differentiate with respect to the square root of x and then multiply by the derivative of the square root of x with respect to x. So we need another chain rule on this. And then let's write that square root of x as x to the 1/2. Okay, so this is correct. Now let's simplify the derivative of cos, which is minus sine. Let's put the minus in front. Okay, so the derivative of cos is minus sine. I put the minus over here. Now the derivative of x to the 1/2 with respect to x is 1/2 x to the 1/2 minus 1, which is minus 1/2. Okay, I'll pull the 1/2 out there with the minus. And we can write minus 1 over 2 root x, because x to the minus 1/2 is 1 over the square root of x. And then we have cos root x sine root x. Okay, let's ask Mathematica to do that also. What? Where did the half go? Oh, I see. I forgot the 2 in here. Okay, so the derivative of cos squared is 2 cos. And so that brings a 2 down here. And so there's a 2 up here, which gets canceled there. And we end up with exactly what Mathematica has. Minus cos of root x, sine of root x, all over root x. Okay, great. Let's move on to question 23. So in 23, we clearly need the product rule. So y equals 6 sine of x cos of 4x. Okay, so y dash is 6 sine x times the derivative with respect to x of cos of 4x, and then we swap the order of these. The 6 comes along, okay, so we've used the product rule there. So next we want to simplify. This requires the chain rule. This one is very easy. So we've got 6 sine x. Now the derivative of cos gives minus sine. So let's put our minus here. we've got minus sine of 4x, but then we need to multiply by, using the chain rule, the derivative of 4x with respect to x, which is 4. Okay, so there's the chain rule used on cos of 4x. Now the derivative of sine is cos, so we have plus 6 cos of 4x cos of x. And so we just need to simplify, bringing this 4 over. So minus 24 sine x sine 4x plus 6 cos 4x cos x. Okay, question 24. We have y equals x minus cos squared of x all to the power of 4. Okay, so here let u be equal to x minus cos squared x. So dy on dx, or y dash, is equal to the derivative with respect to x of u to the power of 4. So du to the 4th on du, du on dx, but u is this. Okay, now the derivative of u to the 4th is 4u cubed, so we have 4 x minus cos squared x all to the power of 3, and then the derivative of x minus cos squared x is 1 minus 2 cos x times the derivative of cos x, because I'm using the chain rule on this, so times minus sine x. Okay, I need to simplify this by multiplying the two minus signs, and then let's bring this out to the front. So we have 4, 1 plus 2 sine x cos x, and then times x minus cos squared x all cubed. Okay. Oh, I think that was question 25. Okay, so I have skipped question 24. So next I need to do question 24. Which is t equals 1 minus 3z over sine pi z. Okay, so for this one we need the quotient rule. So t dash with respect to z is equal to, now if I let this numerator be u and the denominator be v, then I have 1 on v squared v du on dx, or sorry, on dz, but that u is 1 minus 3z, and then minus, we swap these around, so sine of, no, that's my v, isn't it? So 1 minus 3z d on dz sine of pi z. Okay, and so this derivative is minus 3. So 1 on v squared minus 3v. Now this derivative of sine of pi z is pi cos of pi z. Okay, where v is equal to sine of pi z. Okay, let's move on to question 26. Y is equal to 5x sine of 5x plus cos of 5x. Okay, so we've got a sum of two things, but we can see we'll need both the product rule and the chain rule to do this. So y dash is equal to 5x d on dx of sine of 5x plus 5 sine of 5x d on dx of x. So that's the product rule on the first term. And then let's just write d on dx of cos of 5x. Okay, so we'll need the chain rule here, and we'll need the chain rule here. So we've got 5x. Now the derivative of sine is cos, so that becomes cos of 5x. And then we've got to multiply by the derivative of 5x. So this is times 5. And then I'll just copy down 5 sine of 5x from above. The derivative with respect to x of x is 1. Put times 1. And then the derivative of cos of 5x is minus 5 sine of 5x, having used the chain rule, multiplying by the derivative of 5x. Okay, so we just have a little bit of simplifying to do here. So 5 times 5 is 25. So 25x cos 5x. And then these two are like terms, so 5 minus 5 is 0. So this should be our derivative. Let me get Mathematica to check. Okay, Mathematica agrees. It's 25x cos of 5x. So let's move on to question 27. Which says, show that the fourth derivative of sine of x is just sine of x. Okay, so we've got to differentiate sine 4 times. So the fourth derivative of sine of x is the third derivative of what is the derivative of sine x? It's cos of x. So the third derivative of cos of x. Okay, and so that is the second derivative with respect to x of the derivative of cos of x, which is minus sine of x. So we can pull out that minus sign. And so this is now the second derivative of sine of x times minus 1. And so this is minus the first derivative of the derivative of sine, which is cos of x. And then the derivative of cos of x is minus sine of x. So we have minus sine of x, which is sine of x. Okay, so that's done. Alternatively, you could just differentiate this 4 times and list out what your derivatives are. That's probably conceptually easier from your point of view, and show that you get sine of x. Okay, next one, question 28. Find the derivative of tan. Well, let's express tan as sine of x over cos of x. And so label u sine and v is cos. So y dash is 1 on v squared, v, which is cos, du on dx, so d on dx sine of x, and then minus the other way around, sine of x d on dx of cos of x. Okay, simplifying these two derivatives. So we have 1 on v squared, cos times the derivative of sine. Now the derivative of sine is cos, so this is cos squared x. And the derivative of cos of x is minus sine, but there are two minuses, so that's plus sine squared of x. Cos squared plus sine squared is 1, so we just have 1 on v squared, which is 1 on cos squared x. So this is our derivative, but there's a name for 1 on cos. It is sec x. So we can write this 1 on cos of x all squared, and 1 on cos of x is sec of x, so this is sec squared x. Okay, question 29. Differentiate this with respect to x, so that's taking d on dx of 2xy cubed. Okay, so what we need to do is be very careful to use the product rule here. So 2x times the derivative with respect to x of y cubed, and then plus the other way around, 2y cubed d on dx of x. Okay, next let's simplify this, but we need the chain rule here. So 2x dy cubed on dy, dy on dx, and then dx on dx is 1, so this is plus 2y cubed. Okay, let's simplify this. The derivative of y cubed with respect to y is 3y squared. 3 times 2 is 6, so 6x y squared. Let's write that dy on dx as y dash because it's smaller to write. And then we'll copy down what remains, the 2y cubed. Okay, so we've got that derivative now. So let's move on to question 30. Something similar, differentiate with respect to x, y squared over x plus 1. Okay, similarly, we'll use the quotient rule. So we've got 1 on v squared, v, d on dx of u, which is y squared, and then subtract the other way around. Okay, and so let's simplify this. 1 on x plus 1 squared, and then we have x plus 1. Now we need the chain rule for this, so that's dy squared on dy, dy on dx. Now the derivative of x plus 1 with respect to x is just 1, so this is minus y squared. Okay, so one more line. 1 on x plus 1 squared, x plus 1, 2y, y dash minus y squared. And we're done with that question. Okay, question 31. Says differentiate implicitly to calculate dy on dx. Okay, so we have 14x minus 7y is equal to 112. And so what this means here is to apply d on dx to both sides of the equation. So let's say applying d on dx to both sides, we have 14 d on dx of x minus 7 dy on dx is equal to d on dx of 112, which of course is 0. Okay, so simplifying this, dx on dx is 1. So we have 14 minus 7 y dash equals 0. And then we're asked to calculate dy on dx, which is y dash. So we want to simplify this. So we'll take this minus 7y dash to the right hand side and then divide both sides by 7, and we'll get y dash, which is dy on dx, is equal to 14 over 7 is 2. Okay, question 32. Implicitly differentiate x squared plus 2y squared minus 11 is 0. So again, we'll apply d on dx to both sides. So differentiating x squared gives us 2x, and we have plus 2 d on dx of y squared, and then minus the derivative of 11 is 0. This is equal to 0. Okay, dy squared on dx is what we need to simplify. So we've got 2x plus 2 dy squared on dy on dx. So the derivative of y squared with respect to y is 2y. So we have 2x plus 2 times 2y times y dash equals 0. Okay, we're asked to calculate dy on dx. So let's take the 2x over to the right hand side. Y dash is minus 2x over minus 4y. Now, provided y is not 0, sorry, that's plus 4y we're dividing by, we get minus x over 2y. Okay, let's do the next problem. Question 33. We've got x to the power of 2/3 plus y to the power of 2/3 is equal to 5. And we've got to calculate dy on dx using an implicit differentiation approach. All right, so differentiating x to the 2/3, we bring down the 2/3. We have 2/3 x to the power of 2/3 subtract 1. And then similarly, we will need the chain rule on this, but it will end up looking the same as this, because when we use the chain rule, we break it up in this way, and then this derivative looks just like this, except with y's. Okay, so 2/3 x to the power of minus 1/3, and then 2/3 y to the power of minus 1/3 times y dash is 0. We'll multiply both sides by 3 over 2 to cancel the 2/3. Take the x to the minus 1/3 over to the right hand side, and we'll get y dash equals minus x to the minus 1/3 over y to the minus 1/3. Okay, let's move on to question 34, which is our last one. I need another sheet of paper. So in 34, we've got x cos of 2y plus sine x cos of y equals 1. And we've got to apply d on dx throughout. So here we need the product rule. Here we're going to need the product rule. So x times the derivative with respect to x of cos of 2y, and then plus cos of 2y dx on dx. And then we have sine of x d on dx of cos of y plus cos of y d on dx sine of x equals the derivative of 1 with respect to x, which is 0. Okay, now we need to simplify this. So this one requires the chain rule. So x derivative of cos of 2y with respect to y is minus sine 2y times 2, and then multiplied by y dash, because we need the chain rule there. Now this derivative is just 1, so we have plus cos of 2y. And then over here we're differentiating cos of y with respect to x, so we need the chain rule. So this is plus sine x. Now the derivative of cos of y with respect to y is minus sine y. And then we need to multiply this by dy on dx, or y dash. Okay, and then finally differentiating sine with respect to x gives us cos. We have plus cos y cos x equals 0. So we need to tidy some things up now. So we have minus 2x sine y of 2y times y dash, but there's another y dash over here. So let's put minus sine x sine y. We'll put in brackets that y dash, and then we've got these two remaining, which we can take over to the other side of the equation and say minus cos 2y minus cos y cos x. Okay, it says find dy on dx, so we just have to divide by this term now. And so we get y dash equals, now the minuses in both or all will cancel, and so we can express this as cos 2y plus cos x cos y all over 2x sine 2y plus sine x sine y. Okay, and we're done with the problem set. Thank you.